Hi guys, in this video we'll go over KineFX for procedural motion design, and I won't be going through any character animation stuff, just motion design. So first of all, make sure you have MOPS and AE11 in your Houdini so you can follow along. And first we'll go through basics and I'll go through these examples I have here one by one. And yeah, let's start. So let's start with the basics first, and I'll drop a line. Maybe give it 10 points. Then a rig doctor. Now you can see this looks like a skeleton. Let's test it by also dropping a rig pose. Yeah, now if I do this, everything that's down the line moves with it. So this is how a rig works. So a rig is basically a skeleton made of joints and bones. And in KineFX, these points are the joints, and these lines are the bones. So there's also a hierarchy of parent points and their children points. So if I just reset this, so this is our point zero. This is the parent point of point one, which is in parent point of point two, and so on. So if I do anything at point one, the the children of this parent will also inherit those attributes. If I like, I'm rotating here, or I can scale it, sorry, translate it. And even if I scale it, that also will go through the whole rig. All right. Another thing to keep in mind is that a point can have multiple children points, but a point cannot have more than one parent points. If a point in some case do have more than one uh, parent points, it would result in a cycle error. Let me show you an example. I'll get another line. I'll So you can see what happening here. Okay. Yep. You can see it is working fine. There are no errors. But if I connect these two endpoints, uh, yeah, now you can see I have multiple closed loops here. So if I go here, there's an error. Hierarchy traversal failed, compute hierarchy result found cycle. This is the cycle I was talking about. Because as you can see, if like, let's think about this one. So this one has a parent point, which is this one, and maybe these are its children points. Okay. But then this point has multiple parents. Like this could be the parent or this could be the parent. And therefore, this cycle error. So we have to make sure in however we create our rigs that these cycles are not created. We have to be mindful of that. And other than this, there are attributes to majorly this transform attribute, and there is also another one, local transform, which when you do anything here, like as you see this, it should be generated automatically, maybe not in here, but in the workflow I'll go through later on, it will automatically generate the local transform attribute. So the transform attribute is basically a point transform with in 3D space, and the local transform attribute is a point transform respective of the point's parent point. Okay, so like this point's transform would be 3D transform would be whatever wherever it is in the 3D space, but its local transform will be relative to this point, which is its parent point. That you have to like keep in mind a little bit. And when we do custom operations in Vex or Wops, we do operations on local transform and not on the transform attribute. So if you see here, I initialize transforms. If even if I don't, it kind of does that internally on its own. Like there are no transform attributes here. Transform attribute it created on its own. So now let's go to examples. Let's go in. Here I took a box, just a regular default box. Get some points from volume, currently 0.05. Sort them by y-axis. Add point index attribute, which I think I won't be using later on, so not that important. Then I get a start group 0.0, which is right here. Then I set a path cost attribute, just a cloud noise, nothing too fancy going on here. Then I connect these points with this node and find the shortest path from the start to all the non-start points using this path cost we just made. Use these points, drop a polypath to rebuild the curves, transfer the start group over, then get normals along the curve, a rig doctor, initialize these transforms. Then I use this MOPS spread fall off to animate a fall off that we will use later on to animate our rig. As you can see, yep. Then I also set a rotation axis, which is just a inverted normal. Now here I'm making a float scale. This can also be a vector, by the way, the scale. But since I'm working with uniform scale, float is good. So I'm just creating a channel ramp based on MOPS fall off here. So you can see now what happens if I place this. See, the rig is scaling according to our fall off attribute. This is like quite easy and pretty basic, and scale is not the only thing here. There are more functions like rotate and translate. The three main things are scale, rotate, and translate. And in this example, since I made it a long time ago, I used this scale function rather than the pre-scale function. But since then, like the more I've used this, I found out that pre-scale is better to use instead of scale, because the scale function can sometimes give you weird issues. Like it is not having any issues in this particular example, but I think it is better to use pre-scale. Yeah, pre-scale, pre-rotate, pre-translate, all those things. Okay, so then I copy 2 points, and this box is referencing the size from this points from volume. And this is so there are no gaps or anything. Like if you see at the end no gaps, it completely fuses together. So this is this, and example I made another box, points from volume, sort by Y, same thing. Here also path cost, shortest path, fuse, polypath, group transfer, get normal, MOPS fall off, spread fall off. Yeah. So here you can see the same thing. Rig doctor. Then I also calculate this rotation axis, and then I blur MOPS fall off in proximity mode. So now look at this, and without this blur, is it even doing anything? Okay, maybe, yeah, the color is set here. Let's visualize this from here. Yep. So without the blur, with blur. So here I'm doing all three things. I'm rotating, scaling, and then translating this. So first let me show you only the rotate. So rotation needs an angle and a vector axis. Angle is float, vector axis, and angle is in radians. So between 0 and 1 and not like 360, 0 and 360. So angle here is our channel ramp of 1 minus f at MOPS fall off. Why is it 1 minus MOPS fall off? Because when our fall off is 1, we want the angle to be 0, and when fall off is 1, we want it to like rotate fully. Then we have our scale, which is also just based on this ramp. Our rotation is here. And then last we have translate. Like, so translate is a vector. First I give it the direction. Here it is normal, along which direction to actually move these points. Then I get this channel ramp, again 1 minus fall off, because when the fall off is 1, we want the points to snap to their original positions. Then I also multiply with a float to control how much translation is actually happening. Yep. So you can see as the fall off spreads through the rig, things kind of rotate back into place, right? If I were to look at this, as you can see, as we scrub along, things fall into place. Then there is our scale function. Again, this was made a long time ago. I didn't know about the difference between pre-scale and pre-scale. So better to use pre-scale and all that from now. So if I only scale, you can see this is happening. Then I add this translate a bit. So you can see I just used it a little bit to offset the pieces. You can use it a lot as well. And like get this effect where it's kind of spawning from nothing and then assembling. So if I incorporate all these things, now you can see it is working a bit more as expected. Also, let me get this translate back down. Yeah, this is more like. Okay, so this is our basic example. And also one thing, you do not have to use shortest path for this. There is another way. I'll show you in later examples, which also will work here as well. Uh, so we'll go on to the surface next. So first, make whatever object you want here. This is a very basic rock. Add the path cost attribute. Get a start group. Here I have like multiple points. Then I use random selection by count to make sure there is only one, like just one start point. Same thing as we did earlier. Shortest path, use polypath, transfer our attribute and group back. Then I'm also getting a point normal from the actual geo and transferring it here, renaming it to geo underscore n. Then get the normals along our curve. Then here I make my custom transform. Like thread transform is make transform at normal and this up axis, universal up y axis. Then I made the axis attribute, which is a cross product between a geometric normal and a curve normal, and I just multiplied it by -1. So rig doctor has no errors, which means the rig is okay. Then I do this fall off, as you can see, from start point and spreading outwards. Then I blurred it a little bit. Then I took this incoming rock, converted to VDB, and reshaped it, dilated it quite a lot. Then I am doing a reprojection of this. Like, as you can see, this is reprojecting to this expanded SDF, and as the mops fall off grows towards one, it goes to the original position. What I'm doing here is taking this gradient of the SDF, negating it, then the value of the SDF, and multiplying them together, and then adding it to the original point position coming here. Then I mix between this new position and the original position based on fall off. That's what creating this effect. Then in the rig attribute angle, again, now this is one of my newer examples. So I'm using pre-rotate and pre-scale and not just rotate scale. So as you can see, now it's kind of unfolding, and without this, it would be just a little bit nearer to the rock. But I am doing this so that there is enough space and it's not actually kind of going through or intersect the actual shape. But it's like art direction, you can do it however you want. So our rig is ready. Okay, so then we time shift it to the end frame where everything is as we want it to be in the end. And here I'm taking this rock, splitting points so that each polygon has its own unique points. Then I assemble those, create pack primitives, plug it into the first input of joint capture proximity. In the second input, we need this rest pose, and in third input our animated rig. So here we have this, then bone deform, and you can see like this is KineFX is working on like the surface now. Then I unpack and fuse them and get the normals. Okay, so this is the surface. Let's go to our third example. Okay, the third example is fractured geometry. So here I start with a big subdivide, normal, ice offset, scatter some points, fracture them. It will take a bit of time, so I've already got it here, logged in. So this RBD connected faces, if you don't know what this does, uh, let me just refactor this. Yep. So as you can see inside, these are a lot of fractured primitives, and if you try to render glass or subsurface, like these inner primitives then will show up as cracks. If we do not want, we append this RBD connected faces. It does its calculation, it's working on primitives, and uh, then there then we append this later on, like we can test it out right now, like that. It gets rid of the inner primitives that are inside the geometry. That might be an issue when rendering glass or anything like that. So this is here set to delete connected, and I'll show you in a bit. It doesn't just delete everything that was inside. It kind of deletes based on this threshold. Like if the distance that has been recorded here in this primdist attribute, if that and the current prim dist is less than this threshold, then only it will delete it. So okay, let's go ahead. So I fractured this, assemble, we have it here. Then I add, append the add node, delete geometry, but keep the points. I won't use this scatter points because as you can see, these are very different points, not the same. So if you're doing this to your pack geometry or your fracture geometry, make sure to get points from your actual pieces. Then I take a start group. Is there one? Yeah, here it is. Then here I'm setting up, like earlier I said that shortest path is way to get, like this is the second way. So here I set this prop attribute at only at the start point, other would be prop 0. Then I append this AE propagation solver. Like if you just search prop solver, you will get it here. So here everything is default, I think. Yep. So what this does is this is more or like an infection solver, but the advantage of using this infection solver instead of like pyro burst spread or anything is that it also stores the ID of the infector point. Like if point A is infected and point B is not infected, and then point A infects the point B, so the point B will have the attribute of ID of point A stored on point B as well. That is our infector attribute, which will be used like later on. I'll show you. So I time shift at the point where all of these are red. Like, yeah. Then I make polylines. For this, what I did was if I at infector is not equal to -1. Now let's have a look at infector here. Only one point is -1, which is 7764. This is also a start point. That means our start points will be will have the infector attribute -1, and uninfected particles, uninfected points will also have the attribute in -1. That means there are no parent points to them. So we make polylines. If it's not -1, we get a point which is ID2 point, 0 and I at infector. Then we add a primitive 0 polyline, and from our PT, this parent to the current point. It is important to make this to make the direction of the prim from the parent to the child, like from the parent point, which is we got it here, to the current point, which is the child point. So if we don't do this, the vertex order like gets reversed, and later on like the rig would fail. Let me show you. Like if I do this, the rig has failed. Count cycles. It basically now doesn't know which way is forward and which way is back, so it gets confused. So yeah. After this, orient along curve, get our normals, and here I'm again making the trans. Then the same thing from, just a second. Yeah. From the start point, we start spreading out our mobs fall off attribute. Then here I'm getting this axis. So the rotation axis, I'm using a curl noise here, and it is important to normalize your axis attributes, otherwise it goes a bit nuts. Here again, the same thing. You can see this rig kind of unfolding. Again, then time shift 300. And this time, instead of using any those KineFX specific nodes, this is what we need: transform pieces. What this does is it takes our assembled geometry in first input, our animated or deforming rig in second input. It doesn't take a rig, it takes points with transform attribute, but yeah. And in third input are rest points. So we get this after we transform our pieces. Okay, so then we unpack. Now you can see inside like all these shattered bits. So if I also do this, so now you can see as they start getting close, the interior uh, the interior primitives get deleted when they come close together. Yeah. So that's it for this video. And if you have any questions, drop them down in the comments. And yeah, that's all. Thanks for watching. Bye.